it's going to be a big year for sort of increased kind of government involvement around the internet and kind of related technologies. And that touches a whole host of really interesting things. So one of them is on encryption. There's a huge fight kind of brewing in Congress right now about sort of the ability for law enforcement or the government generally to have backdoors into encryption. That's going to have a big effect on sort of security and anonymity online. In Europe, there's a huge initiative called the Digital Single Market, which has potentially a big impact on how devs can collect and manage user data, particularly if you have users that are in Europe. And that's not to mention sort of the safe harbor that you might have heard of, which kind of controls sort of what privacy regime user data goes into. And in copyright, there's also this huge case that's going down. It's sometimes called the sort of World Series of IP that looks into whether or not sort of the declarations in an API can be copyrighted, which has really big implications for like competition, your ability to kind of re-implement APIs, and a number of other things that sort of devs do on a local basis. And so at the sort of government public policy team, one of the things we noticed is that these sort of decisions are being made in government actually pretty far away from the developer community, and sort of devs and people with a technical background don't actually speak with a big voice on these issues in DC. And in our mind, that's actually really critical, right? Because one of the problems is that without sort of a dev voice and without technical expertise, there's sort of government and regulatory decisions that are being made without kind of a full grasp of the technology. And so there's a risk of kind of making poor decisions that make the kind of technical ecosystem worse. And so one of the things our team has been thinking a lot about is how we bridge this gap and how do we get sort of the developer voice, the technology voice, people with kind of knowledge about how these systems actually work, sort of into the regulatory picture. And in our mind, it's really a two-pronged problem, right? So the first one is kind of an information friction problem, right? Which is devs don't really have the time to focus on what's going on in government all the time. They don't know necessarily how they can influence this situation, and they don't necessarily know where they can be most effective. That's one big issue. The other big issue is the kind of lawyers, not coders problem, which is that people doing policy, even people on the Google team, so I'm actually a little bit unusual, I'm like an ex-software developer kind of turned policy person. They're largely lawyers, they're largely ex-government people, and so they don't actually immediately think about bringing sort of devs on the ground into these kinds of conversations. And so one of the things that we've been thinking about, and we'd love to get everybody's kind of feedback on, is this idea that Google actually has this huge internal organization around policy, right? We have people paying attention to these issues full-time, all across the world, every single issue, and tracking them all very closely. And so one of our ideas is by sort of exposing this organizational infrastructure to devs, we could actually kind of solve these problems, right? On the informational side, we could get information that's relevant to devs to them before sort of these decisions get made. And we can also do a much better job about getting kind of dev feedback about what are the issues that they think Google should be taking a stand on, what things we should be doing to better represent their interests in government. And the hope is sort of by doing that, we can actually break down the wall, right? We can actually get more technical expertise into these policy debates and actually hopefully make decisions that are a little bit better. And so there's really two questions that we're really wondering the most about, and we're basically kind of going on roadshow, where we're going to kind of developer communities all around the world, getting their feedback on two big things. One of them is, what are the issues that kind of devs are most interested in? What are they interested in kind of getting Google to take a position on? And the second one is what's the most useful information to be provided, right? Like on a day-to-day basis, what's useful to know? And we're thinking about a number of things that we might do in terms of making those information channels a little bit better. And so this is a lightning talk. It's only designed to be 5 minutes, so I'm basically over already. But if you're interested in this sort of thing, we're hosting drinks and dinner at Revel in Fremont tomorrow evening. And I've got a few slots left, 4 or 5 slots. So if you're interested in this stuff, you want to talk more about it, maybe be involved, just catch me after all the talks are over. I'm happy to kind of get you looped in there. So thank you very much for your time tonight. Yeah, sure.
Okay, so next we have some speakers from Google Cloud Dataflow. We're going to have Robert come up, but I'd like the whole team to come up and sort of introduce themselves, give a little bit of a talk about what they do. Yeah, you can come.
Certainly isn't the whole team. There's like
No, sorry.
Hey, Robert, why don't you introduce yourself?
Okay, yeah, so I'm Robert Bradshaw. I was on kind of the internal version of Dataflow before doing the external version of Dataflow, and then we've got these folks here and probably another several dozen folks who are all behind the scenes making Dataflow actually work. So.
Hi, I'm Sam. I'm the tech lead on Dataflow, and I worked on Millwheel before that. So I like big data.
Hi, I'm Steven. I work on the monitoring infrastructure for Dataflow, so helping users understand what happens from there. Well, after they've run their job, what's going on?
Ruben, I work on the streaming part of Dataflow and work on Move before that.
I'm Rafael. I'm the technical program manager of Dataflow. So we're happy to be here and tell you about this technology, which you're about to hear about from Sam, and we'll stick around in case you want to chat and connect.
I just wanted to attach some faces with the names here. So if you guys have any questions after or during, I guess, in your quiet voice presentations, these are the guys to talk to because they're here to help and give us information. So if you want to take it away, Robert.
Okay.
So I'm assuming the slides are going to show up eventually. But
You're all plugged in.
I'm so used to the whole Hangouts thing.
And your screen is shared on the Hangouts.
Not yet.
And I've got my audio muted, so your audio is muted. And I guess the one thing I would ask, if anyone has a question for Robert or for Sam later on, try to get them to repeat it, whoever that is, just so I can hear for the Hangout. Thanks, guys.
Okay. So so I'm going to talk a little bit about Python Dataflow. So I don't know how many of you here have heard of Dataflow. Okay, well it's going to be a lot more by the time this evening is done. So Dataflow, originally we came out with Dataflow in Java. That just seemed the best language. But right now I'm going to talk about something that's kind of sneak peek for something that is in the works, which is bringing Dataflow to the Python language. So it's coming. We don't actually have any firm dates when we're going to release. We'll release when we're ready, but we're working on it. So why Python? Well, there's a lot of advantages to using Python. I mean, any language has advantages, but one nice thing about Python is Dataflow is a very functional programming model, and so that jives really well with it. When you have first-class functions, you can just define lambdas in place. It has more flexible calling semantics. Sometimes the rigid nature of a statically typed language kind of gets in the way when you want to just express your intent. The other thing is, as I'll show you in just a minute, there's a whole lot less boilerplate when you're defining Dataflow things in pipeline for these reasons. There's a couple practical concerns. There's a lot of existing communities, especially the numerical, scientific, computing communities, that have a lot of stuff in Python. They're comfortable with Python, and they have a lot of libraries in Python, and they want to use big data processes because it gets to the point where one machine isn't good enough, and spinning up your own cluster is really hard, but Dataflow kind of takes care of all that for you. Also, Python is one of Google's standard languages. We have Java, Python, Go. And so it's a good reason to release this. Probably the most interesting reason for me is Python is a new language. So we have the Dataflow model, and right now we just have the Java API. And by providing the Dataflow model in a second API, it allows us to kind of tease apart, well, what is Dataflow versus what is its specific incarnation in a language. And I think this is really fun to see like what sticks and what doesn't. So as some examples, maybe I'll take a step back. Dataflow is kind of like a successor to MapReduce Hadoop. That's kind of if you've heard of Spark, it's similar to that, where basically you have really big collections and you're trying to process them in parallel. There's a couple operations you can do. One of them, the basic operation, is parallel do. That's a map. So the idea is that you want to take elements in one at a time and then produce elements. And you can do this. It's embarrassingly parallel. You can do this on as many machines as you want. So this green part here is the Java version, and then this little blue line down there, maybe you can't read it in the back, but even from the back you can tell that it's a lot shorter. So this is our parallel do operation. And most of this is actually boilerplate. You can kind of see this middle line, or these middle three lines are the only ones that do anything. As another example, side inputs. So side inputs is something we have that allows you, it's basically like Spark Broadcast, where you have some information that you want every node to have. And the interesting thing about side inputs is this may be computed in a deferred manner. So you may do some computations, and then you want those computations to be passed to every other computation. And here we have the example of the most succinct way to do it in Java. And then again, Python is just one line. And this is possible because Python has a much more natural way to kind of reason about calling functions and stuff. Side outputs are similarly a lot more succinct in Python. And part of this is due to the fact that you have tuples and dictionaries and lists are very natural objects versus they're very heavyweight. And in Java, you just can't express these things as succinctly. The join operation. So this is the simplest join basically you could write in Java. And in Python, now we've gone to more than one line, but it's still a whole lot less than we had. Yes?
Well, can't you effectively do this, I mean, just as few lines in Ruby, which is a Java subset, which works on top of Java, but will reduce the amount of lines you have to do, which is very similar to Python.
Yeah, so there are explorations with Ruby. There's also explorations with Scala, which it makes it more compact, but there are things about if the API is written in Java, it contorts the API to make things easy to express in Java, and then even if you're using another interface for it, that doesn't mask away all the things. So like the method names and the way that we use builder patterns and all that kind of stuff.
Ruby is a layer on top of Java, so literally, if you write it in Java, it will conform to Ruby every single time, 100% of the time, with tiny exceptions.
Yeah, I guess it's more about the fact that
not so with Scala. That's why I mentioned Ruby.
Yeah. As an example where this is difficult, though, for instance, with side inputs, this map function takes an arbitrary number of arguments. And the Java version doesn't take an arbitrary number of arguments because the arguments may be heterogeneously typed. And if you wanted to use Groovy, you would have to have a layer on top that translates between this nice, just throw all your arguments at the end into the Java thing. So yeah. Yeah. So you'd have to have a lot of convenience methods, which is certainly a direction to go. So the other thing is p-transforms, kind of the core building block. So if you're writing in a language, your core building block is functions. So you don't have to like copy and paste every time you want to do something. You just call a function. Kind of the equivalent in Dataflow is a p-transform where you encapsulate a bunch of operations, and then you can call it multiple times, and make libraries of these things and so on. Much simpler to do in Dataflow. And the nice thing about this is it's all the Java goodness, except for it's a different language. So so you have batch processing, you have streaming processing, you have windowing, you have triggers, and so everything works the same. The monitoring works the same. The optimization all works the same. But it's just a different front end that is more natural to work with. So I'm going to do a really quick demo, if it works. So here we have Cloud Dataflow. Just do an import. And then here I did a map. So I just squared the numbers, and the output is what you would expect. Here I do a group by key. So group by key is the big shuffle operation that takes pairs, and it says, okay, for the first thing, give me a list of all the values that are associated with that. So here I see I'm mapping things to their length, and I'm saying, okay, here's the strings that have 1, and okay, cool. And here's over here is everything that has 2. And group by key is kind of the workhorse of all your aggregation, all your grouping, and everything like that. Zoom in, yes. Actually, the full screen, that is probably a lot more legible for someone like you. Just being 50 feet away. I'm a lot closer. Okay, so here's a little bit bigger example. So we have the famous Shakespeare Hamlet poem, and we want to count. This is defining a custom transformation that does count, and it just says, okay, take every input, make a pair where the second element is 1, and then sum all those ones together across grouping by those inputs. This is kind of a count, and then we can use it in our pipeline. And here's our output. This is all the words with their counts. Yeah.
I'm just going to ask why 2 and 14 if they're all going to be 1.
They're not all going to be 1. Because what we do is we group and then we sum. Yeah. So after this first thing, they're all going to be 1, and then we do inside the count. Last example. So this is a little bit more involved example. This is what you do if you're actually writing a program. Is you create a pipeline object. You can pass a whole bunch of options about how you want it to execute, what kind of machines to use, everything like that. And then these pipes operators is kind of like Unix. It's a little hard to see on the screen. There's actually, those are all pipes. It's a whole bunch of operations, and I'm writing out to a file. And then I run the thing, and it runs either locally or on the service, or we actually have it's kind of a pluggable implementation, so you could have other runners. And then here's an example of it actually wrote this file out. So there's one thing I want to mention, that is not having types actually is a little bit of a disadvantage. Because the way the Dataflow model works, or pretty much any programming, but especially the Dataflow model, is you build up these composable transforms, and then when you wire them together, you want to know, do they match? And the interesting thing is, when you're wiring your pipeline together, you're not actually sending any data through. The data gets sent through after, when you have a whole pipeline and say, okay, now execute it, because it does a whole bunch of optimization and shipping it off to remote machines, and you really don't like getting some type error on, virtual machine 37 in some log somewhere. And so we have facilities for actually declaring that these transforms expect and take certain types. It's similar to the PEP 484 gradual typing. That can catch your errors before you actually go off and execute it, before any data flows through your pipeline. So, okay, so we're actually looking for people who are interested in trying this out. If you like what Sam tells you about Dataflow, but you wish it was Python, feel free to contact me, and we'll see if we can get you whitelisted. So thank you.
Anybody have any other questions for Robert? Once.
Okay.
So we'll just take a moment to get Sam set up. We'll be good to go. Yours.
Okay.
Sound looking good? Okay. What do I want to do for a picture? Okay. Yes. I'm in the Hangout. Is that going to display? It's not going to display here, or?
You should be able to use that. It's a pixel, right? It's on the other side. What adapters do you have? This is a brand new.
Yes.
Brand new pixel. We have no. What are we going to do with that?
I can definitely get a local presentation to work. So.
Do you know how to make it work?
Yeah. But I don't know if it's going to get recorded then. Should we go ahead with local, or?
If that's what we need to do, yeah.
I can actually also record that. If then you're not going to get a lot of stuff later.
I can try to turn the camera so it has the screen on it, and then you can send me the slides if you want to do it that way too.
Okay, let's try that.
Unless somebody has an adapter. Anybody have any?
All right. So big data systems. So not a lot of Dataflow users out there quite yet. We'll work on that. But how about Spark or Hadoop? How many people have worked with those systems? Okay, so some background. Maybe any streaming systems like Storm or okay, two Storm users. All right. So when we started building Cloud Dataflow, we identified that you would approach big data by choosing a system based on the problem you were trying to solve. So you needed to choose a system if you wanted batch or streaming. You needed to choose whether you wanted accuracy or speed. So for a streaming system, do I want complete results or do I want fast results? And you're compromising things like simplicity versus sophistication. So if you're looking at maybe a database with SQL type language, you sort of hit a sophistication cliff there where you can't express things after a certain point, and then you have to switch over and re-architect your system. And this operationally, if you want to run at scale, you're worrying about, am I wasting machines? Am I using the resources I have? So all these factors went into building Dataflow, where we built a system that you architect once, and then you can choose which of these things are relevant to me, and reuse that same code to optimize for whatever your use case demands. So instead of picking a system that is inherently going to compromise between these, you use this unified model that will allow you to choose and change your mind too, whether you want to batch your data today and stream it tomorrow, whether you want to run at a scale of 1,000 machines today and 100 tomorrow. So that's the essential goal of Dataflow, is to allow you to write your application and then have all the details get out of the way. So Dataflow is a couple different things. It's a collection of SDKs. Robert showed the Python SDK. We have the Java SDK for expressing, this is my data processing job, right? You pick your language, you express your logic. And it's also a managed service that's, in this case, run by Google, but that's separate from what we built in the SDK. So it doesn't have to run on Google. And what this managed service offers is we're going to optimize the execution of your pipeline. And that's why we think it's awesome. So some possible use cases, standard big data things like filtering, transformation, if you're just manipulating data and trying to clean it up. You could also have analysis use cases where you're trying to determine what are the different insights that my data can tell me, and whether that's in batch or streaming mode. Those are the kinds of things you target with Dataflow. So this is all pretty heady and abstract, and talking about what the managed service offers is, so you've written your pipeline, and now you need to actually deploy this at scale. And the state of the world right now is oftentimes you do a lot of performance tuning and handling, okay, my sharding function is no longer working with this data size, I need to redetermine that, change those splits, and I have to spin up a cluster and keep this long-lived state around. And Dataflow handles all this lifetime and optimization for you. So you again just have this job and you say, run my job, and Dataflow is going to optimize its execution, handle worker lifetime, startup, teardown, things like that. And whether it's stream or batch processing, both are going to run just fine. So in terms of accessing the SDK, it's open source on GitHub for Java, Python 2 in development. Will land on GitHub when it's ready. And there's also a community built up around it. So there's a Scala SDK that some folks have developed, also on GitHub. And there are different runners as well. So when I talked about how the SDK and the managed service were two different things, this means that when you start writing Dataflow, you're not committing to Google if you don't want to. So you can write something in Dataflow and run it on Spark, whether it's on Dataproc on Google's cloud, or you can run it on Amazon's cloud. Whichever offers you the best value is your choice. So you can run it on Spark and Flink as well. So we really tried to say we're confident enough in this model that we think that that users will want it regardless of where they're running, and then we think that we can run a managed service that's compelling enough that people will want to run on Google's cloud. Are we doing? People still with me here?
Second, GitHub
second GitHub link. It's looking pretty good. Oh, no, the Flink. Yes, that looks wrong. Excellent. All right, I will not ask, can you in the back read the slides, because now I know. Yeah. Cool. So this is sort of the big picture, but let's talk about a use case. So taking some of the big data services on Google's cloud, PubSub, do folks work with that at all? Any hands for that one? Okay, sweet. Okay.
Yeah,
Okay, cool. So a little bit of familiarity with that idiom, and then Dataflow, and then how about BigQuery? That's okay. Some BigQuery a lot. That's good. So you've got your transport layer here, your analysis layer, and then a giant data lake where you can throw all your results when you're done. So let's think about if I have users that are watching things on their phones. People do that a lot these days. And I'm starting with 16,000 events per second, aggregated into months. And first I want to know, what's the average viewing time over the last 7 days? So traditionally, to answer that question, I'd architect on a batch system and call it a day. I've got a daily aggregate. I'm pretty happy with that. Then maybe requirements change, and I say, okay, now I want to know how many sales happened in the last 30 minutes. And that, yeah, okay, I can still run that on a batch system, run batches of size 30. That's pretty good. Maybe a little bit of tuning to make sure that startup teardown isn't too significant. Then somebody said, hey, let's see how many viewers we had in the last minute. Like, in a lot of cases, all of a sudden, you have to throw out your batch solution and re-architect on a streaming solution, and that's really no fun. So this kind of evolution is one of the things that Dataflow targets, where you can move between use cases like this seamlessly without rewriting your system. So this is just an illustration. You've got your devices sending data into PubSub, and then Dataflow is processing them, putting them in BigQuery for later analysis. So next we're going to do a bit of a deep dive on the SDK. Any questions so far? Right. So a Dataflow job is a pipeline. It's a directed acyclic graph of computations. So you've got inputs in the form of data sources, and then you have these intermediate stages where you're transforming one or more data sets into another, and then at the end you have outputs. So we call these inputs sources, and the outputs sinks, and then the intermediate collections are called P collections for parallel collection. And so you're going to write everything in terms of manipulating these parallel collections.
So are the parallel collections the business one?
The parallel collections are the business data, and the business logic is going to be parallel transforms. So you got to start with some input data. So Dataflow offers standard connectors to things already on Google's cloud, your cloud storage, PubSub, data store. But you're not locked into just those. So you can write your own custom source, and basically the key here is that as long as you tell Dataflow how to parallelize this source and split it into different pieces, then you can get all this managed service magic for free, because Dataflow will be able to parallelize this for you. So if you had a different file format, or if you wanted to read from S3, you write a custom source and be up and running. Additionally, you can write to cloud storage, PubSub, adding support for some more things, adding custom support there. And we have a fair number of native implementations for different file formats. I find a lot of people using Avro, XML as their input formats. And just to take a look at how Cloud PubSub in particular is useful as sort of a streaming source and sink, it allows you to either take a couple different streams and use a Dataflow to combine them, or you could have multiple jobs that are consuming from a single stream. So it adds this layer of indirection where you can have sort of a whole collection of different pipelines that then can have different consumer and producer sets along the way, each of which is emitting sort of a different logical result. And another really good combination here is then to take this data and stream it into BigQuery using their streaming import, so that you always have that data for later analysis. And then you can sort sort of add a fork to your logic whenever you like and add additional analysis paths. So looking at key collections, are folks familiar with RDBs from Spark at all? Because this is going to be a lot like that. So they're either bounded or unbounded in size. Here we have an example of some football fans added this and hijacked my slides. So yeah, I don't know about this happening this year, but maybe with the Vikings disbanding, that could be a thing. But here we've got a collection of different inputs, and you've got these parallel collections can come either from something I'm basically creating statically in memory, or from an input source, or from a transform of another collection. And thinking back to sort of the MapReduce model, oftentimes these are key value pairs. So they can be key value pairs, they don't have to be though, so they can be any arbitrary type. And so how you operate on these is with transformations, and the key transformation is parallel do. So this operates individually on each of the elements, parallelized across all the workers that are running, and allows you to manipulate one key collection into another. And so elements we produce are handled in bundles that are sliced and diced, however is going to be so on. However the pipeline execution requires. But this alone isn't going to be enough to actually write a pipeline. So we'll look at how to do an aggregation next. But the example here is looking at a bunch of inputs. And here we're just keying by the first letter, which we're calling session ID, but returning a collection of singleton elements into key value pairs. So the parallel collection, you can transform that from one set to another. But in order to do an aggregation, you need to actually then group things and combine multiple elements into some kind of aggregate. So this is where the group by key operation is used. And you can then take things with the same key and combine them. So then how you're going to do sort of the traditional MapReduce is starting with a map phase, which is parallel do, and then a group by key, gather everything, and then another parallel do to take everything for a given key and then turn that into an output. This makes reasonable sense for bounded collections, but then there's unbounded collections. And how do I know when I have all the data for a given key? And I might never have all the data for a given key if I'm talking about a streaming data set. So the addition to our API that allows us to reason about streaming data sets is this idea of windowing. So basic windowing is featured in a lot of micro batch systems where you have fixed windows just corresponding to take an aggregate every minute, every 30 seconds, things like that. And you can even imagine doing something like a sliding window where you have the last 5 minutes calculated every minute, something like that. But where Dataflow really shines is sort of unusual windowing functions. So imagining maybe a sessions use case where I'm taking user activity and I want to see, well, what is a grouping of that I calculate, and I want to basically compute everything the user's done until they're inactive for 15 minutes. So now my window boundary is undetermined, and it can span an arbitrary number of micro batches. And so what Dataflow does is it expresses aggregations in terms of keys and windows. So you essentially group by key and window, and this allows you to perform these window aggregations in a way that's meaningful and extensible. And in order to provide a completeness semantic, we have this notion of watermarks, which a source can communicate, whether it's a native source or a custom source that says you have complete data up until this time. So if you're performing some kind of window aggregate, then you can admit that and say, I have complete data. Now, when we talked about early results versus complete results earlier, you can also have speculative results. So you can take a single input stream and say, I want an early aggregate as soon as any data is in the pipeline. And I also want a complete result when that's available. So you can have the single system both compute speculative and complete results. So those are the primitives, but in terms of actually building a pipeline, you want to layer these together. You can't write everything in terms of these primitive transformations, or else your code would be really verbose. So, as Robert talked about, you want to layer things into composite parallel transforms. And these are going to be the functions that you're going to write the transformations for your different parallel collections. So there's some included ones in our SDK, things like count, remove duplicates. You can see how count would be decomposed into primitive transforms like with ones, group by key, some values. But this makes the code more readable, more reusable, and you can sort of use this then as a quanta for determining what your monitoring is going to look like and how you're testing things and that sort of thing. So once you've written your code, you want to run it and see what it does. So we have both a direct runner that's going to run on your local machine, validate, this my code, pass my unit tests, things like that. And we have this managed service runner, and as well as a community runner. So this is the Spark runner, the Flink runner that we alluded to earlier. So you can execute your code in all these different environments with different properties. So locally, you get fast results, but limited scalability. Remote is less visibility, but more scalability. So that's the SDK. And before I jump into the service, any questions? Yeah. Asking how the API is specified. So can you give me a little more detail?
What's necessary to implement my project. So the server and
So when we say client, are you talking about something to submit jobs or a runner? Okay, sure. So the bindings, we haven't done a huge effort to document those bindings quite yet. So this gets into what Robert was talking about, where we are going to extract a pattern from Python and Java. So at this point, there's a large degree of inference there, and we want to improve that story. So that's the state of the world. Yeah.
Are the bindings on the key transforms are on the business logic?
Yeah, so the P transform is going to have the different types, inputs and output types.
Is there a way to extract communication logic away from transforms for distributed architectures so that you can avoid architectural cross-cutting?
So the question is abstracting the communication from key transforms to avoid cross-cutting architectural.
Abstracting communication from the business logic so that you can distributed architecture so that you can avoid an architectural cross-cutting.
Could you give me an example of where you're at?
Well, the API pattern, as it was originally written, is standardized input and standardized output for separation of concern.
Yeah.
But by binding standardized input and standardized output, you're binding a secondary concern of communication logic. Now, by binding that secondary concern of communication logic to that primary concern of business logic, that can only be used in a centralized architecture without sharing that communication logic. But nowadays, we use distributed architectures where we have a separated proxy and separated message queue and things like that. And to share the communication logic and communication functionality in the I/O flow, because we have the request and response being shared across an I/O flow, we can't do that because all that communication binding is down at the controller or the business logic.
Okay,
so they can't see how to request it, they can't see the authentication, they can't see all these things that are bound at the business logic. So what I'm asking is there a way to separate that?
So there's not a way to separate that. I think I might get into maybe some of the intention of your question when we talk about the optimizations of fusing different things together, but we can also follow up offline later.
Okay.
So the Dataflow Service, looking at the lifetime of a pipeline, you've written your job in the SDK, you want to submit it to managed service, see a world, see what it's like. So what's going to happen is this is submitted to a job manager that then is going to spin up compute engine instances on your behalf. These are going to be the workers that execute your pipeline. So once these workers start up, they're going to call back to the manager, request work, and they're going to get a description of, okay, you're assigned this piece of work, update progress, and as that's happening, then you can monitor this using a UI in the Cloud Console. And then when it's all finished, sends them down so the lifetime is fully managed. So that's the high-level view of job lifetime. And there you see the instances spinning up and spinning down. And that is all handled by our service. So what that's going to buy you is exactly once sort of handling of elements. So if you're doing account computation or something, that's going to be repeatable and deterministic based on your input size, regardless of whether you have worker failures or something like that. This isn't to say that if you have side effects to your code, it won't be run more than once if there's a worker failure, but if you're trying to do some sort of deterministic calculation, you can depend on that being executed exactly once. The service is also going to optimize the graph of your execution, and we'll go into some specific examples of that in a little bit. But it's basically allowing you to not worry about hand optimizing your code to run in parallel, and instead allowing you to write more readable and reusable code. As mentioned before, it handles lifecycle management, resource scaling. You can interact with this using the API or command line, and you can monitor your job in real time or look at cloud logging to see sort of an aggregate view of what all your workers are doing. So one of the optimizations that the service is going to handle for you is this idea of fusion between consumers and producers or between siblings. So imagine you have two parallel dues that are happening without any group by key in between. And so an implementation might have a shuffle between them and needlessly move data between machines. And what this is saying is no, these would be inlined and run on the data set at once during a single pass through the data. Whereas with sibling fusion, what it's doing is taking something where you have multiple readers for a given input set and running those against a single pass on the data. So you might be saying, well, it can do all this by hand, and yes, the answer is of course, but then your code becomes less readable, less usable. So by handling this for you, Dataflow allows you to keep code simple, understandable, and shareable. Another one is combiner lifting. So imagine that you're doing a distributed count, and you have a bunch of values for a given key that you're sending to a receiver machine that's going to perform that count. Now, you could pre-compute the counts for a given receiver on the sender, and if you did that, then you'd be sending less data over the wire. And so this is exactly what the framework is going to handle for you. So it takes that, minimizes the amount of communication necessary, reduces the amount of compute used, and saves you time and money. So those are a couple ways the Dataflow service works for you, and the overall goal is to optimize your time. It says that you're programmers, you want to write programs, and all the other details should be taken care of and get out of your way. So that's the story with Dataflow, and I'll be happy to take your questions or talk about use cases. And thank you very much. Yep. Situations where I would not recommend Dataflow versus which? Versus MapReduce or earlier systems. Versus MapReduce, I would probably recommend Dataflow over a MapReduce-like system. I think there are some sort of graph-like computations that would not be a good fit for the Dataflow API as written right now. So if you wanted to do sort of a lot of worker-worker communication, but it's something we're looking at. Yes.
So what if you're like every day using Dataflow and want to see the data? How do the workers, do they come along and go offline?
Yeah, so the question is about, for a streaming data flow, if you have sort of varying load over time. And the way that is handled by the streaming service that we currently have early access to the auto-scaling feature for that. And what it's doing is it's looking at the source and identifying the backlog for that and trying to optimize for the backlog being minimized and at the same time maximizing utilization. So it's looking both at the observed backlog and the observed worker utilization and throughput and trying to optimize between them. And so, yeah, it'll spin up instances and spin them down as it needs to. Yeah, so the user can always decide, well, they can specify a static size for their job. So if they want to over provision because they want to make sure they're always keeping up regardless, that's a possibility. Or as a cost control, you can intentionally under provision too and say, I never want to run more than 5 machines at once because that's my budget. Yep.
So, for your follow-up, you were making a comparison between on-parallel transforms and right?
So I was making a comparison between the parallel collections and RDB.
Okay.
Yeah.
So whatever that equivalent is, have you actually done any benchmarking testing on kind of completeness and resilience?
So in terms of testing resilience and completeness with respect to the Spark ecosystem? Okay, sure. So for batch, I think that there's pretty much parity between them. I think where there's some differentiation is on the streaming side for use cases like sessions, where trying to do that with a micro batch model is pretty painful, it turns out. And so I think that the streaming primitives that the Dataflow exposes are one differentiator. And we've got sort of some side-by-side case studies that we're going to blog about this. Right? Anything else? Going once?
So maybe one follow-up. So what
Yeah,
would you
sure.
say is the biggest edge?
Sure. So the edge between this and what's offered by Amazon and the Spark stack. So I think the streaming model is the biggest edge at that point, and closely followed by the idea of no ops and not having to hand tune your pipeline. At the same time, if you've got Spark code, we're more than happy to have you run that on cloud platform on the Dataproc system. So Spark or Hadoop.
And you've got the SDK to run on your phone. You can't download Amazon stuff.
That's true. Okay. Yes. So yeah, the code being open source is also definitely an asset. All right. Great. Thank you very much.